Section 3.3, multiplication and division of whole numbers. And today we're going to take a look at the division of whole numbers. Which is here. For any whole numbers A and B, where B is not equal to 0, we can talk about dividing A divided by B and it equal to C, if and only if C is the unique whole number such that B times C equals A. We call A the dividend, we call B the divisor, and we call C the quotient. Okay, so this is something akin to what we did with subtraction. In fact, it's almost identical. When kids first learn to do division, they rely heavily upon what they know about multiplication. So for instance, they know that 2 times 3 equals 6, right? That's a multiplication fact that they memorize. So if they're asked to find what is 6 divided by 2, the equivalent question to ask is 2 times what will equal 6? What is it? What's missing? And of course the answer is 3, so the answer to the division problem is also 3. And that's exactly what this says. The way that I get A divided by B is I say, what do I have to multiply by B? Right? What does this number have to be in order to get back to the divisor A? All right, so what we're going to do next then is we're going to take a look at the models for division. There are two models here, the first two models, that feel very similar. They're a little bit different. Your book does not distinguish between them, which is fine, but I want to make sure that you're aware that there is a slight difference in them because it's the structure of how they're set up. First one, this is the set partition model. So Junie has 24 rocks. Oh, by the way, let me make a comment. We're going to use the exact same word description. Like the problem itself is going to be exactly the same on all of the models we're going to do. I think we're going to do four models. It's almost the same description on all 4 models, or maybe the same description on all 4 models. The difference is almost in how you think of it. Okay, so the problems are very, very similar. Junie has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each one get? Okay? So we've got 24 rocks, and we've drawn rocks before. So let's draw 24 rocks, okay? All right, I've got 24 rocks. She wants to give them to her 6 friends. So she's going to collect them. And how is she going to collect them? What is she really doing with these rocks? She's going to divide them into groups. How many groups? 6 groups, exactly. So she's going to create 6 groups out of these blocks, right? Out of these rocks, yes? Okay, so if she guesses the wrong number, so like let's say she gives each of them 5, she's going to have a few left over and she's going to have to reevaluate, right? Okay, you guys know the answer. The answer should be 4, right? So in this case, she would have given too many away and one of the friends wouldn't get anything, so she'd have to reevaluate. So what we're going to do is we're going to make 6 groups, and in making 6 groups, we're going to find that we can only put 4 rocks per group. So the whole key in this model is that we know how many groups we have, we just don't know how many rocks are in each group. All right? So write yourself a note that the idea here is that we know the number of groups. We know the number of groups. Okay, a variation to this. This one looks slightly different, the word problem itself. All right, again, Junie has 24 rocks. She bags them together in groups of 6. If she gives one bag to each friend, how many friends will receive a bag of rocks? We've got our same rocks as before. But this time, what is it that we know? Yeah, we actually don't know how many groups we have technically. What do we know? We know the number in each group. You guys with me? So this time what we know, I'll finish answering the question in a second, but what we know is we know the number per group. Okay, so that's slightly different, right? And in reality, that makes it easier to actually do the problem in terms of the visual here, right? I actually know I need to circle 6 of them at a time. Whereas in the other one, you guys knew you needed to circle 4 because you were using prior knowledge to actually make that claim. Agreed? But what you actually knew is you knew how many groups you'd have, not how many were in each group. So the answer here, of course, is, I didn't write the answer on my last one either. This is 4 friends, right? It's the number of, the answer is the number of groupings that you have when you're done. The answer on the problem before was actually what? 4 rocks. Same answer, but it's not the same units. It's not answering the same question. It's 4 rocks. All right, so let me pause real quick here and make the comment with you. This is exactly what people do when they put people in groups and classes. Like teachers. You're going to be teachers. You have to make a decision when you're teaching. Do you care about the number of kids that are in the group or the number of groups that you have? And there may be a specific reason why you care about one versus the other. So let me give you an example. I tend to worry more about the number of people in a group. And the reason that I do that is because I feel like that if the group gets too big, somebody's probably not working in the group. They're just listening to everybody else, or they're off in la la land. Make sense? So when I make groups, I tend to focus on making sure that I have a specific number of people per group. So my magic number is 2 or 3. All right? There's a problem with that, because if you had a classroom of, say, 20 kids, 25 kids, we'll do 24 because it divides nice. So 24 kids, and you really thought, gonna do groups of 2. So 24 kids, groups of 2. How many groups do you have? 12 groups. And there's how many of you in the classroom? 1 of you in the classroom. And somehow you've got to make it around to all 12 groups if they start to have problems, right? So sometimes it may be more practical to have the groups a little bit bigger because there's only 1 of you to make it around to every single group in the class. Are you guys with me? So you either decide groups of 2 or you do something like this. You say there's only 1 of me, which means I can only get around to 6 groups in my classroom, 4 groups in my classroom, 8 groups in my classroom, and you do something like this. We're going to number off 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, which means I know when I'm done I will have 4 groups because they only had 1 through 4, right? Okay, so those are the 2 variations of what's going on here with this model for division. There are 2 more models for division, though. This one is the missing factors model. So this more talks about how to solve the problem in terms of the definition for division, kind of. So this is the idea that says that if I have 24 and I want to divide it by 6, so the problem's the same. It says 24 rocks. She wants to give them to 6 of her friends. How many does each friend get? The question is simply asking you, what would you have to multiply 6 by to get 24? Right? That's the definitional approach to division. And of course the answer here in the box or blank is 4. 4 what? It was 4 rocks in this example, right? 4 rocks. Are you guys with me? I wrote it wrong. I didn't even see it right. Yes, I do mean 24 divided by 6. Thank you so much. I wrote it right once, just not twice, huh? Yes, 24 divided by 6. Yes, Alyssa.
So we won't be able to tell if it's a missing factor model just by reading the question.
No, these problems are far less about, I mean, you can distinguish the difference between these 2, although they're just variations of the same thing. They are actually different models, and they actually had different names in one of the books that I've used before. Your book doesn't do that. They don't even talk about them being 2 different things. But yes, on these, they don't distinguish by the language and the problem. It's how you work it, exactly, which is quite different than the other models that we've done, isn't it? Yeah, it really is. All right, so repeated subtraction. This one is a very interesting approach. We're going to come across repeated subtraction again in the next chapter, or the next section of the chapter, but we're going to be doing it from a little bit different perspective there. And I often, when I have tested on this particular question before, have people revert to this section right here when they think about repeated subtraction. So when we get to repeated subtraction again, I'll make this point one more time. This kind of repeated subtraction I'm talking about here, they're the same. It's just that I'm working with small numbers here, okay? And when I do it again, I'm going to work with bigger numbers and show you a variation on what happens when their numbers are larger, all right? So small numbers, repeated subtraction. This model actually is much better than describing this over here. We had to guess, if you will, educated guess, I know, but we had to guess when we made 4 of them per grouping, right? All right, so what we're going to do over here is what we would really do if we were probably this child handing out these rocks in the classroom. We would have our 6 friends sitting around them, right? And we'd say, here's one for you, and one for you, and one for you, and one for... We'd go down the list, right? And we'd say, oh, look, I still have rocks left. Let's do it again. You guys with me? This would also be just much more fair because then everybody gets to pick a rock or something, right? I have fairness as one of my quality traits, you know, like the strengths finder things. So like this just speaks to me, this method. This is what I would do. We would be fair about it. All right, so here's what it looks like in terms of working out the problem. I have the 24 rocks, and I give each of my friends a rock, which means I gave away how many rocks? 6. And I subtract, how many rocks do I have left? 18. And then I do it again. And I give away 6 more. And I subtract, and I get 12. And I do it again. I give away 6 more, and I subtract, and I get 6. And I give away 6 more, and I subtract, and I get 0, or at least something that's too small to take 6 away from. So I know I made the mistake inadvertently before, but if this had started out with 26, at the end I'd have 2 left over, and I couldn't do it again. I just have to have 2 left over. So my answer ends up being how many times I subtracted 6, hence how many rocks each kid got. And the answer to this would end up being 4, because I subtracted 6 4 times. So they each got 4 rocks. They each selected 4 times from among my rocks.
So are we going to know which method we're supposed to use?
Yeah, it will tell you in the problem.
Okay.
Yeah, no problem on that one. Yeah. Okay, so I made a comment here. I've already said this, but let me read it too, just for the sake of having done so. 3 of the 4 models above do not represent different types of word problems, just like Alyssa and I were discussing, right? As they did with subtraction, for example, but they represent different ways of solving the same word problem. So I think everybody's here. No, we have one person gone. Kelsey's gone today. So I need you to get nearby with somebody. So I'm going to have you move up here with Jessica so she doesn't have to move. We got 2, 2, and then 2 and you 3. Okay, so Hannah and McKenna and Gretchen. All right, so what you're going to do is you're going to create basically 2 word problems, okay, right? There's really just 2 word problems you're going to create, the first model and the second model. And then you're going to solve them, because that's the difference on this one. I haven't had you solve the problem on the other ones because that wasn't really the point. The point on this one is the solving part of it, okay? So, and as you do this one, we won't do this one out loud when we're done. I'm just going to come around and make sure everybody's on the right track, okay? So go ahead and take a look at creating 2 word problems solved in 4 ways. All right. We're going to finish on up this section. Finish this section on up. Get my words in the right order. Whole number properties for division. So we've talked about whole number properties for addition, subtraction, and we found out there really weren't any, right? Multiplication, we had a whole bunch of them, and now we're going to do division. All right, so it says which of the following properties hold for division? So again, what closure means is being able to take 2 numbers in this system, which we're working the whole number system, and combine them with this operation and seeing whether or not that number is still, in this case, a whole number. So what do you think? Is that going to hold for division? All right, so if it's not, let's give an example of why not. So what's going to fall apart on this one?
3 minus 7.
Okay, but we're doing division.
3 divided by 7.
That'll work. 3 divided by 7. This is not an element of the whole numbers. We're going to have fun with some notation here. You guys are still working on a test where you're using some of this notation, but not an element of the whole numbers. It does not give you a whole number, does it? It gives you a fraction. It's called a rational number, but it's not a whole number. So no closure property. How about commutative? No. Can you give me an example? What was it?
5 divided by 9 and 9 divided by 5.
Okay. So, in fact, I'm going to change the number just a little bit. I'm going to use 10, just so that one of them actually works. 10 divided by 5 would actually be a whole number, right? That would actually work. But if I did, I get 2. If I do 5 divided by 10, I get 1/2. The real issue here is that these are not equal. But, of course, we don't even end up with one of them being a whole number when we reverse it, right? So it fails like twice. Yeah, multiple failures. This is not going to work. Okay, associative's a little bit harder to sort of discredit just off the cuff than those two were. So let's create an example that we'll try and figure out for this if this works. And as we create it, what we're going to do is we're going to try to get the numbers to be whole numbers to make sure that at least it doesn't fail on that count at first. So let me try. Let's do 12 divided by 4, and then we'll do divided by 2. So if I did 12 divided by 4, what do I get? 3. 3 divided by 2 would be 3/2, not a whole number. But let's try it in a different order now. 12 divided by 4 divided by 2. So what's 4 divided by 2? 2, and then 12 divided by 2 would be, it's what? 6. Yeah. So again, multiple failures because these two do not equal, and one of them is not even a whole number. We could have created the problem so that it were a whole number. I mean, that would be a possibility. We're still going to fail on the fact that they're not going to be the same. So this one again is a no. What do you think about the identity? If there were one, what would it have to be? 1. It would have to be 1. Because if I divide, say, I've already got a 12 on the screen, so 12 is in my brain. 12 divided by 1, I get 12. And that's at least one part of the identity property, right? But what, you made a face for me, Amy. What happens? Yeah. This doesn't work the other direction, right? 1 divided by 12 does not equal 12, which is the whole point. I should be able to get back the same value if it's really the identity element, and it has to work from both directions, and this simply does not work. 0 property. Do you remember the 0 property for multiplication? What did it say? You multiply by 0, you get 0. So this one is, again, and it has to be on either side, right? 2 times 0, 0 times 2. So in this one, it would have to be division, right? So if I divide 0 by any number, what do I get? 0. That works just fine. But what happens when I try to do this one? Yeah, 2 divided by 0 is what we call undefined. It does not have a value. And I'd like to talk real briefly about why that's the case. I know you guys know that sort of definitionally. You see that and you say, it doesn't work, undefined, does not exist, some version of that. Let me talk about why this is true, though, from in terms of the definition of division. The definition of division says that whatever this number equals, if it were to equal something, would have to be arrived at by taking 0 times that quantity and getting back the number 2. What's wrong with that? There is nothing I can multiply by 0 that's ever going to get me back to 2, right? That's why this is undefined. According to the definition of division, there is no such number that works. The definition of division doesn't work with it. So that's why we call this undefined. All right, so 0 property doesn't work. Distributive property. All right, so we're going to do an example. I've got one written down because I want to try and keep my numbers as whole as possible along the way. So I'm going to try the example of 20 plus 10, and we will divide by 5. And then we'll do the same thing. I don't mean plus. Yeah, I do. I do mean plus. And then we'll do 20 divided by 10 plus 5. So in other words, we're looking at what happens from both directions. If I were to do division as the last part of this property, and I tried 20 actually, let me write it that same way. The 20 divided by the 5 plus the 20 and divide by, sorry, not 20, 10. 10 and divide by 5. Okay, so this is checking one direction. Actually, let me move this. Whoops. Okay, so let's do the left-hand side. If I do what's on the left-hand side, what's 20 plus 10? 30. And what is 30 divided by 5? 6. Okay, let's do the left-hand side, or the right-hand side. What's 20 divided by 5? 4. And what's 10 divided by 5? 2. So 4 plus 2 is 6. So in this case, when I do the division second, it works, right? So one direction of this did work. So we're going to check the other direction now. So what I should be able to do is I should be able to take this and I divide it individually. So 20 divide by 10 and 20 divide by 5. So let's do this over here. What is 10 plus 5? 15. So what is 20 divided by 15? It's not a whole number. It's exactly right. So let's see what happens on the other side. What's 20 divided by 10? 2. And what's 20 divided by 5? 4. And that one actually is a whole number. So these are not equal by the sheer fact that there's a whole number on the right and there's a non-whole number on the left. They also happen, of course, just not be the same number, but one of them is dreadfully not a good number because it's not in the whole number system. So final analysis is much like subtraction. None of the properties hold for division. None of them work. Okay? All right, we have one more example. JJ. JJ claims that the following is true by the distributive law where A and B are whole numbers. 3 times the quantity A times B is equal to 3 times A times 3 times B. How would you help him out? I've seen this mistake made lots, actually. This is a pretty common one. In fact, some of you may be looking at it and going, I'm not even sure what's wrong with that. That's okay.
Well, because you have to distribute on the right side of the equal sign, you have to distribute just like you distribute.
If that were true, right?
Yeah.
If that were true, we'd have more distribution going on the right. So what's wrong with what he's thinking? Yeah, so he's trying to distribute over multiplication, right? Yeah, and we don't have a distribution of multiplication over multiplication. What does multiplication distribute over? Addition or subtraction. It actually works as well. So the first issue that we would probably want to make is that distribution is multiplication over addition or subtraction.
So if he was given just the 3A times B,
Mm-hmm.
his problem would lie in the fact that he's multiplying the two together and not adding them.
Say that again, Alyssa.
If he was given just the left side, the 3, and then A times B, his problem on the other side would just be that he's multiplying them together.
The problem on the other side would be, these would not be equal.
Okay.
These two are not the same value.
Okay.
Okay? Okay, the issue on the left-hand side is that we have 3 things that are multiplied together, right? Do you have a property that allows you to change things when you've got 3 things multiplied together? You do. Careful. Commutative, right? The commutative or the associative properties. In this case, it's actually associative is the one. Associative is one where you have 3 things multiplied together, and you can regroup where the parentheses are. So the only property that applies here, not the only, but the property, we'll say the primary property that applies. Is the associative property. In other words, we could take the 3a times b here, and if we wanted to, if there were a reason for doing so, we could regroup the 3a together and then do the b after that. That's something we could do here. That all is sort of theoretical. I mean, that whole statement that I just made here sounds like a bunch of mathematical talk. What could you do to show him that his method isn't really not going to work, though? What could you actually do to show him this fails? Numbers. Yeah, we put some numbers in. We try both sides with the numbers in for A and B. Now, usually when that happens, using the numbers 1 and 0 are not good choices because things sometimes work with 1 and 0 that don't work in general. So let's, try some numbers that actually fail to work that aren't, giving numbers that are 1 and 0. So for example, we could let A equal what? You guys pick one. 2 I heard, so we'll let B equal 4. I heard a 2, I heard a 4, so we'll go with that. So if we let A equal 2, and let B equal 4, this is the left-hand side. So what is 2 times 4? 8. 3 times 8 would be 24. Okay, so this is the left-hand side. We'll do the right-hand side over here as well. The right-hand side, he tried to do, is to take the 3 times the 2 and the 3 times the 4. So what is 3 times 2? 6. And what is 3 times 4? 12. And maybe off the top of your head, you know your 12s tables. Anybody? 6 times 12? 72. These two are not equal. Can you tell exactly by how much they are off of each other? What's the catch here? How are they related?
There's an extra 3.
Yeah, this one is multiplied by an extra 3. It's exactly 3 times 24. The reason I pointed out is because that's the problem. The problem is we had an extra 3 on the right-hand side. And that's what caused it to sort of be incorrect, if you will. All right, so this right here would actually be showing him why it doesn't work. Both of those features are important to talk about with students, both the general case of what's going on and the explicit case, I think, is very practical because it actually shows them that you're not just making up more math stuff. You're not just using language to sort of dissuade them from doing what they did. You're showing a concrete example. All right.
Well, in that case, to then the associative property to show that they were
It very well could. You definitely could show them the associative property being more helpful there. That would be a good example. Do you guys understand what Hannah's suggesting? So we mentioned right here that this piece actually is true. And you could show them that that's true using that same 1 and 2, or not 1 and 2, 2 and 4 that we used for A and B, and it actually working for you. Yeah, that would be a very practical thing to show them. I agree.